Hello and welcome to another video from HPart. Today we will be talking about designing point source collection lenses. These lenses are used to image a single source into an optical fiber. One common place they appear is in a technique called LIBS. LIBS is short for laser-induced breakdown spectroscopy. Here is a lovely image from Wikipedia that shows the general idea. You take a laser, you shoot it at a sample, it vaporizes part of the sample into a plasma, you collect the light from a plasma into an optical fiber, run it through a spectrometer, and analyze the resulting light. After you complete that analysis, you get valuable information about the elements that were in the sample that you shot with the laser. Today in this video, we're going to talk about this element right here. This is the point source collection lens. It's imaging this plasma into this optical fiber. So let's get started. The first thing we need to do is create an emitter that will represent our plasma. This will be a point source emitter, and we're going to put it at the origin. Next, we'll make a point source emission. We're going to make this range between 200 and 1000 nanometers. This would be a common wavelength range if you were doing something like LIBS. And we won't put any simulation restrictions on it for now. Now let's go ahead and cast it. So you can see this is the light coming out of our point source. It's heading uniformly in all directions, uniformly across the 200 to 1000 nanometer wavelength range. Now the next thing we need to decide is the working distance from which we will image this light. And I'm going to go with 100 millimeters because it's a nice round number and it's generally useful for laboratory work. So let's go ahead and create a revolution that will represent the first element of our lens. Before I create this element, I want to talk briefly about the high-level design that we're going to create. If you watched any of the previous videos, you know that we can use a single PCX lens to collimate light into an optical fiber. Well, as it turns out, this design is essentially just two PCX lenses back to back. The first PCX lens takes the light from the point source and collimates it, and then the second PCX lens takes that collimated light and focuses it back down to a point source, or in this case, our fiber. So now that we have the basic idea of what we're going for, let's get after it. I'm going to put this lens roughly at 100 millimeters. We're going to start with NBK7. We'll change it later. And I'm going to increase the thickness to about 5 just to give us a little bit more room to play. And go ahead and create that lens. So this is our first lens, which we're going to look to collimate this light. Now let's go ahead and create the second lens. The second lens will be rotated 180 degrees. We're going to put it roughly at 110 millimeters, give a little spacing. We'll increase the thickness just a bit. And there we are. Now let's make the spacing here precise. So first I need to set the spacing between our emitter and our front lens to be exactly 100 millimeters. So I'm going to create a spacing formula. I'm going to call it S01. And I'm going to go ahead and set my anchor to be point source 1. And then reference B will be body 1. And I'll set that to precisely 100 millimeters. We see how that the lens moved a little bit. Then I'm going to set the spacing between these two lenses. Now, if you recall, I mentioned that the light, after it exits this first lens, should be roughly collimated. That means the spacing between these lenses doesn't matter that much. So we're going to leave it fixed and not optimize it during our design. So here we go. We've got our first reference, will be the first lens. Our second, and I'm going to just use 5 millimeter spacing, which should be good enough. All right, there we go. So we got our 5 millimeter spacing. And now we need to place the detector. Now the detector is going to represent our optical fiber. And for an optical fiber, there's a very key number you need to know, and that's the numerical aperture. The numerical aperture determines the cone of light that the optical fiber will accept. If you launch light at a steeper angle than the numerical aperture allows, it will not make it into the optical fiber, so it's pointless. For instance, if we place the optical fiber right here, then light coming from this part of the lens would have to travel at a very steep angle to reach the optical fiber and would almost certainly be rejected. To calculate this angle precisely and to place the detector well, we're going to open up a note and we're going to title it NA Calculations. You can tell I've done this before. And let's just go ahead. We're going to use a numerical aperture of 0.22, which is common in large optical fibers used for spectroscopy. Then we're going to compute the half angle that is implied by that numerical aperture. We're going to ignore the index of refraction for now because we're in air and it's nearly 1. And we're going to see that in degrees. So our half angle is about 12.7. Now based on that half angle, we are going to compute this length here just using some simple trigonometry. And so that length is going to be the radius of the lens, which is essentially this leg of the triangle, divided by the tangent of our half angle. And that gives us 55 millimeters, which is where we will place our detector. You could back it out a little bit and you get slightly better performance, but for now 55 millimeters is good enough. I'm just going to quickly tidy this up, and then I'm going to pop our detector, rotate it 180 degrees. I'm going to shrink its dimensions just so it's a little bit more parsimonious with our lenses. I'm going to put it out at 150, and there we go. Now I'll create the spacing. Go for S2D from our second body to our detector, and we're going to have an initial spacing of 55 millimeters. So that will cause our detector to move a bit, and this is the rough layout of the optical system that we need to design. So now let's go ahead and add that detection to put the simulated fiber onto the detector. So we're going to have two gates. The first will be numerical aperture, 0.22, and the second will be the circular boundary representing the fiber. We're going to go with a 400 micron fiber. Go ahead and create that. Now if we zoom in on our detector, we can see that we've got our fiber represented by that circle on the detector face. All right, now that we put all that together, let's go ahead and cast the light. Now, that was not a very satisfying result. Most of the light is just being cast in a uniform sphere, and very few of those rays are actually making it into the optic. So we're wasting a tremendous amount of our simulation time launching rays that are never going to get to our fiber. So let's go ahead and edit our point source, and let's create a simulation restriction with the nearest target cone. So that's going to restrict the rays that are simulated to the cone that matches the face of this lens. Now that we've done that, let's recast, and we have something that looks a lot better. Now we notice we've got some stray light that's coming through here that's bouncing back off of these lenses. And we don't care very much about stray light for this design, and it just muddles up the view. So I'm going to go ahead and add a light path to get rid of that. Let's get started on this light path by grabbing these surfaces. Oh, badoop. Badoop. And badoop. All right. And then I'll grab that detector. So now the light path has been created. I'm going to drag it up here, and I'm going to add it to the point source. Great. Then I'm going to set the display to hide stray rays, which has hid everything because those rays were cast before the light path was added. And I'm going to recast the light path. And now this is looking a lot better. We can see that we're not focusing on the fiber, so most of the rays are probably missing it. But let's start by seeing how well we're doing. We're going to add a collection efficiency analysis. Detections only, filter the stray rays. That's all good as it is. And let's run it. So what we can see is basically nothing is getting into the fiber. And only about 0.27% of the light is actually making it to the lens. Now that seems like a very small number. Or sorry, is only 0.27% of the light is making it to the detector, which sounds like a very small number. But to understand that better, we need to figure out how much light is actually making it to the lens. So to do that, we're going to open up another note. This one will be maximum collection efficiency. The reason I'm titling it that is we cannot get a better collection efficiency than at the detector than the best collection efficiency we can get at the lens. And we're going to estimate that easily by looking at the surface area of the sphere, because we're emitting a sphere, that is defined by the distance between this emission and this nearest surface of the lens. So that radius is 100 millimeters, because that's how we designed it. And the surface area of that sphere is going to be 4 times pi times 100 millimeters squared. And that's our denominator, which I'll just call D for denominator. And then our numerator, which I will call N, is the area of this face. And that's going to be pi r squared. And, oh, can't use that because N is used for newtons. So I'm going to try NU. And of course it thinks pi is a function because I need to include a multiplication symbol here. Now that I've done that, I'm getting a reasonable result. So now I'm going to create our collection efficiency max, which will be our numerator, over our denominator, and I want to see that in terms of percent. Let's go ahead and create that, and we can see that the maximum we could do would be 0.39% of the total emitted light. Now that may sound like a very low number, but that's the percentage of the surface area of the total sphere that this lens takes up. And we just can't do any better than that. Now you may have noticed that you've seen this number before. So if we go ahead and run the collection efficiency, you'll see that 0.38% is shown as the simulated emitted intensity. So maybe we haven't seen that number exactly, but pretty close. And this makes sense because what's happening with the simulated emitted intensity is the system is looking at all the rays that might make it into this lens. And that happens to be 0.38% of the total, which is exactly what we calculated over here. So if we take a look here, the full story is as follows. We could do about as well as 0.38, 0.39%. But currently, we're only getting 0.27% of the total light to our detector, and essentially 0% of that light is actually making it into the fiber. So that is the starting position that we are trying to work from. Now let's set about improving it. The first step is to create a merit function. We're going to go ahead and add a target. We're going to go with soft efficiency. This is the smooth version of the scaled efficiency, which you want to use for optimization. Our target is going to be our maximum of 0.39. We'll declare it as good enough if we're within, say, 0.36. And we only want to penalize if we're below the target. Now, as far as optimization variables are concerned, let's take a look at our optical system. This distance here between the emitter and the lens is fixed. The distance between the lenses doesn't really matter because the light is roughly collimated, so that's fixed. And the distance between the final lens and the detector we could vary, but if you watch some of the earlier videos on coupling collimated light into an optical fiber, you'll know that as we just keep moving this out, at least on the computer, the number gets better. But it has real-world consequences. It makes a longer tube, it makes the result more finicky to mechanical alignment, and so we're not going to do that. We're actually just going to limit the tube length to what is necessary based on the numerical aperture of the fiber. So all the distances are fixed. That only leaves these two radii. So let's go ahead and add them as optimization variables. Now that we've added them as optimization variables, we're going to bound them. We're going to have pretty wide bounds. I'm going to let them go all the way down to the minimum, and then all the way up to, say, about 100. This is just going to let us be surprised by the optimizer if it wants us to, but I don't think that it will. So we're going to go ahead and create that merit function. Then we'll create an optimizer. We'll use CMAES. We'll set it to sequential because we have a light path. We'll go with max evaluations of 5,000, just so we don't terminate early. We'll go ahead and create the optimizer. I'm going to move this over here so we can see it. Now let's run the optimizer. And we're done. Took about, 300 evaluations? So that has now been completed. And now let's take a look. Well, first we can see that there are a lot of violet rays that are missing the fiber quite badly. So we can already suspect that our UV performance might not be that good. And this also looks a lot like the chromatic aberration that we saw in earlier videos. Now let's take a look at the collection efficiency. We can see that we're still at about 0.38 as our maximum. And the amount of light that's hitting the detector has gone up to 0.28%. And our detection intensity, this is the light that's going into our fiber, has improved dramatically from 0 all the way up to 0.18%. So we've made a remarkable improvement. And for many designs, this might be good enough. But before we can really determine that, we'd like to know how we're doing across the range of wavelengths that our source is emitting, i.e. 200 nanometers to 1,000. So I'm going to create a new source and a new analysis coupled to that source so that we can use it with a scanner. So here we go. And I'm going to create this as a single wavelength distribution. The reason for that is that if I have a single wavelength distribution, I can actually scan across this variable. Whereas with a uniform distribution, I cannot scan. So we'll go with single, call it point source single, just to distinguish it from point source 1. And I'm going to create an analysis, a collection efficiency analysis, to go with it. So we want point source single. We're only interested in detections. We want to filter stray rays. Oh, it's warning us we forgot to put a light path on point source single. So let's create that analysis, then let's go fix that. Good, we've added our light path, and now let's go ahead and run the optimization. Now you see it's launching a lot of sodium light, and we're actually doing better collecting the sodium light than we were collecting the broad spectrum. That shouldn't surprise us. I'm also going to modify the display so we don't have to see this sodium light. So I'm going to uncheck that. Okay. So now we're ready to create our scanner. I'm going to go ahead and open it up. And we want to scan across the wavelength. So there's our wavelength. We're going to start at 200. And we're going to go up to 1,000. And we'll do it in 50 steps just so it's smooth. And the output we care about is the second collection efficiency scaled. Go ahead and create the scanner. And now I'm going to run it. Okay, so what do we notice? Well, two things. First is we're not doing very well down here. We're basically getting no light in the ultraviolet into our fiber. And as we can see from our screen over here, it all seems to be focusing before the fiber and totally missing it. And then on the other side, we notice we have this flat top here, followed by a fairly steep drop-off. And it'd be good to understand why exactly that's happening. So we're going to start by exploring this issue, and then we'll move on to exploring this one later. And then we're going to talk about how to fix it. So this issue over here, we already think we know the answer, which is the light's focusing over here in the ultraviolet. But let's take a look just to see if that's the case. To do that, I'm going to modify the display so we can only see the single wavelength source. Now this is currently at, I think, 550 nanometers, and we can see that it's focusing near the fiber. But what would happen if we change that down to 200? Save it, recast it. You see a pretty dramatic shift in the focal length. Well, now all that ultraviolet light is focusing many millimeters ahead of our fiber, and very, very little is actually making it in. Now in libs and some very bright applications, you might actually be able to get away with this. But here we're going to assume that you cannot. So how do we fix this? Well, the first thing we can do is we can pick a better material. We're going to go ahead and do that, even though it will change the shape of this. So let's get started on that. I'm going to close the scanner, and I'm going to go into the Materials tab. Now, we need to pick a material that has a good transmission properties and good index of refraction in the area that we care about. So to that end, we're going to look for a fused silica material. Now I happen to know that these are some good choices. So we're just going to go with the NIFS-A. If we take a look at that, this has a broad wavelength range covering what we want. It has a good dispersion curve and a great extinction curve for the area that we care about. Now I'm going to go ahead and assign that to both of the bodies. All right, now I'm going to recast the emission. And what we can see is that the point of focus for the UV light has moved a lot. Now let's just take a look and see where the focal point for the infrared light has moved to as well. We can see that that's fairly far beyond the detector. So even with a better materials choice, we still have a lot of chromatic aberration. Nevertheless, now let's rerun the optimizer with our new material. All right. So now that we've rerun the optimizer, we can see we've made some slight changes. And now we're going to take a look at how we're doing. So I'm going to show the optimized source. We can see that the cone of rays that are missing is smaller, which is a good thing. Now let's take a look at the collection efficiency. Go ahead and run that. And we can see that some things have changed. First off, we can see that the detector hit intensity has gone up from 0.27 to 0.32%. That's this number right here. But we'll also notice that this number, the actual amount of light that has reached the fiber, hasn't budged. But let's dig into that a little bit deeper by running the scanner again. So if we take a look, we can actually see that a dramatic difference has occurred. With the NBK7, this area was effectively zero. There was no light reaching the fiber. But now we can actually see daylight in this curve. And for many applications, that's good enough. We can also notice that the shape has become a lot clearer. There's now a single peak, and there's a different shape to the right of that peak. So now that we've gotten at least some boost from switching from NBK7 to fused silica, we're going to analyze why we have a different shape on the left side of the peak versus the right. To do that, we're going to start with a wavelength that's on the left side of the peak, namely about 800. So let's go ahead and change our point source single emission to 800 nanometers. I'm going to go ahead and save that and cast it. We're going to modify the display so that we can only see that one. And here we go. So if we take a look at this light that's right on the other side of the peak, I'm going to have to zoom way in here. And this is hard to see on a video, but essentially where this cone intersects the detector is almost exactly the same and ever so slightly smaller than the fiber. Then if we move to the actual peak, which is at 869, and recast it, the diameter of this cone is nearly equal to the fiber. Now it might be hard to see on the video, so let's open up a spot size analysis just so we can make this official. So we're looking at detections only. I'm going to set a threshold of about 50% just so we can really narrow in on this cone. And I want to use point source single. I'm going to run it, take a quick look. So let's see here. This is actually pretty tight, so I think 50% was the wrong choice. Let's go with the default, 88%. And we'll go ahead and rerun this. Yeah, there we go. That's a lot better. Now what we notice here is the 88% boundary is 0.3897, which is very, very close to the actual diameter of the fiber itself. In fact, if we were to increase this threshold a bit, we can probably get it even closer. Maybe 100%? Yeah, at 100% we are only what, 2 microns away from matching the fiber diameter perfectly. So that tells us something very important. This peak occurs at the wavelength where the cone from that wavelength matches the fiber diameter. And once we know that, and we know that the cone, as the wavelength increases, starts moving to the right, we can understand why these curves have different shapes. Essentially, on this side, as the wavelength increases, we're driving the cone towards the fiber and we're filling up more and more of the fiber. But once we get on the other side of it, the cone, where it intersects the detector, is actually larger than the fiber, and so we start to exclude light, and that's why it drops. All right, so now we have designed and optimized our system. We've analyzed the collection efficiency, and we've also understood how it behaves at different wavelengths. Let's go ahead and open that collection efficiency one more time. All right. So these are our final values. Out of the 0.38% that we could have gotten, we're getting about 0.32% to the detector. And of that, about 0.18% is actually getting into the fiber. For many applications, this is good enough, and we could stop here. But of course, we are going to try one more thing. What could we do to start to get this value up even a little bit more? And the answer, especially which should be apparent if you'd watched some of the earlier videos, is we're going to use achromats. What's keeping this down is chromatic aberration, and we saw that earlier in this video. The UV is still focusing ahead of our fiber, and the IR is still focusing behind the fiber. If we could reduce this chromatic aberration, we could get this value up potentially a lot. So we're going to go ahead and create a new design where we investigate this more fully. All right, here we are in our new design. We're going to start with a blank canvas. We're going to rebuild the scaffolding of the previous design, but we're going to split the front lens element and the back lens element into UV capable achromats, and then we're going to optimize the design again and see if we can improve things. So let's get started. First, I'm going to go ahead and create my emitter. I'll just work from left to right. All right, that'll be at the origin. Then I'm going to create my first revolution. Now this is going to be the left lens element of the left achromat. Now for that, we're going to do a meniscus element. We'll leave these as they are for now. And I'm going to put that just as a placeholder out at about 100 because we had 100 millimeter focal length. Now something I am going to do here that is different is the most common combination for a UV achromat. The flint element is actually fused silica, and the, with quotes, crown element is calcium fluoride. And we're going to follow that here. So I'm going to use a Nikon fused silica glass for our quote-unquote flint element and go ahead and create that. So there's our first element. Then I'm going to create the second, which is going to be a BCX lens, and that'll be, go ahead and make that a little thicker. And that's going to be calcium fluoride. I'll use the Nikon calcium fluoride that's in here. And I'm going to go put this out at 95, just so we can see it. Looks like that was not far enough, of course. Sorry, I meant 115. There we go. Then I'm going to essentially do the same process but mirrored for the second achromat group. So that'll be another BCX. Make it a little thicker. I'm going to put that out at 150. I'm going to set it to our fused silica glass. All right. And then finally that meniscus lens. This one will have to be rotated 180 degrees. It'll be calcium fluoride. And those will be fine for now. And we're going to put that out at, what was it, 175. Okay, there it is. And then we're going to throw our detector just way out there at maybe 250. And we're going to rotate 180 degrees. There it is. So now we have a very spaced out version of our original optical system. And I'm going to start throwing in some of the finer points. First, I'm going to go for the light path. I'm going to grab that surface, this surface. It's a lot easier to grab the surfaces when they're spaced out. This one, this one. Actually, hold on. Yeah, okay, good. That's rotated. That one, and then finally the detector. Okay, so just to check, left, right, left, right, left, right, right, left, because we rotated, and the detector. Correct? All right, now let's go ahead and add the correct spacing to all of these elements. All right, so we had 100 millimeter focal length, so S01 is going to be 100. We'll move that between the two. Then we're going to do S12. And for these UVA chromats, because the fused silica has such a low coefficient of thermal expansion, it's a bad idea to cement them. Because if the lens goes through thermal cycling, the fused silica is just not going to expand at all, whereas the other element might expand quite a bit. And that could cause a lot of cyclic stress on the cement, causing it to eventually fail. So we're just going to have an air-spaced achromat to avoid that problem entirely. Put a small amount of spacing there. Then we're going to create another formula for the spacing between the pairs. That'll be S23. That'll be 2, that'll be 3, and that spacing we'll just leave it at 5 millimeters. Again, the light between here should be roughly collimated, so the spacing is not critical. Now we'll do the spacing between lens 3 and lens 4. That's going to be the same as the spacing on the front doublet. That'll be 0.25. Okay, and now finally we're going to do our detector spacing. We're going to do exactly the same spacing as we had in the previous design, which was 55. Got it? All right. So there we go. We have our initial setup. Now we're missing one thing, and that is that the radii on these achromats, I want them to be, at the interface, I want it to be constrained to be the same. So I'm going to create a formula for both. I'll call the first one AR1. I'll create a free variable, which is the radius, and I'll put that into the formula. So that'll be our achromat radius 1, and I'll do the same thing while I'm at it for the second one. So this will be achromat radius 2. All right, got that. I'm going to drag it into place, and it looks like I forgot to drag a few of these into place, so I'll get that done now. Great, that's looking good. Now I'm going to set these formulas to work. Okay. All right, so the radius on the right should be AR1, and then the radius on the left should be AR1. And then for body 3, the radius on the right should be AR2. And then this one actually will be the radius on the right as well because it's rotated 180 degrees, AR2. So now that we've added both of these, we need to go ahead and add our emission, which was a point source emitter. It was uniform. It was between 200 and 1000. Now we've got that. We're going to make sure the light path is on it, which I forgot to do. Okay, and now we are going to cast the emission. Let's go ahead and cast it. All right. Well, we have a reasonable setup, and we can see that the light is focusing well ahead of our detector right now with the default values. But no worry, we're going to start by adding our analysis and a merit function, and we'll fix it. So we want a collection efficiency. Oh, looks like I forgot to put the detector in. So I'm going to go ahead and add, or sorry, I forgot to put the detection in. Let's go ahead and add that for our fiber. Oops, I forgot to add the other gate. That'll be a circular boundary. 0.4. Good. Okay. Put that up here. There we go. Now let's go ahead and add that collection efficiency and analysis. There we go. Got our detector. We want detections only. Filter the stray rays. And now let's run it. Okay, well, we're getting all of one ray hitting our fiber so far. But we're going to make that a lot better. So let's go ahead and create that merit function. And we want to use the scaled efficiency. And then as far as the optimization variables, we've got more than we had for our first design. We've got 1, 2, 3, 4, 5, 6. And they're all radii of curvature. So I'm going to go from left to right. We're going to go with body 1, radius of curvature, then body, oh actually the next one would be AR1, then body 2 radius of curvature, then body 3 radius of curvature, then AR2, then body 4. Okay. Now the next thing we're going to do is we're going to constrain the limits of these. So I know from prior experience that depending on how the optimization goes, these outer two surfaces can actually get very flat. So I'm going to allow those radii to get quite large. And then I'm going to allow everything to get fairly small. These I'm going to constrain just to make sure they stay curved and we don't end up with any degenerate solutions where this meniscus turns into a flat plate. Then this is 2, this is the right radius, so we'll just stick with this somewhat wide bounds. We can see if it starts hitting one side or the other, we may increase them. Alright, so this is body 3 left. That's going to be the same kind of wide bound. Then we'll do the exact same thing in the middle. And then this is, it says radius left, but since it's flipped, it's on the right. And we're going to let this one actually go up quite a bit in case the optimizer decides to use it to make the outer face flat. All right, we've gone ahead, we've created our merit function. Let's calculate it. So we see we only have one collection efficiency. It's very low. Let's make sure we did soft. Oop, that was scaled. That's the wrong one. We always want to use soft for optimization. As far as the target, well, if we recall from last time, the best collection efficiency we got was 0.32%, so we'll put a target of 0.4, and I'll be happy if we can get the collection efficiency up a little higher. And sorry, I misspoke. For the last project, we got 0.32% hit the detector, but it was 0.18% that actually got detected. And so the good enough value here, I'm going to put it as 0.3. All right. Oops, I'm going to save that, recalculate, and that looks pretty good. We still don't only have one ray hitting, but we'll make that better in a hurry. All right, so now we've got our preliminary design laid out. We have our merit function. The next thing to do is to create an optimizer. We're going to go with CMAS. We'll go with sequential. I'm going to let it have a lot of evaluations. We'll probably stop it early. I'm going to zoom out, and I'm going to move this over into the corner so we can see it. Now, without further ado, I'm going to run the optimizer. And away we go. See, it didn't take very long. We're still dropping pretty slowly, but we'll converge soon and then we'll stop. You can see, as I mentioned, it's making one plate quite flat, while the other is more of a meniscus lens. You can see it here. This is rising. The optimizer will probably stop once it figures out that it can pull this all the way up to the bound. There we are. And now we've hit our convergence point, so I'm going to go ahead and stop the optimizer. All right, well this is looking pretty. We notice that there are very few rays, violet rays, that are exiting the light cone. Most of it is heading directly into the fiber. So I'm feeling pretty good. Now let's check moment of truth and look at the collection efficiency. All right, that's a marked improvement. We'll notice we've gone up from 18% to 21%. We can also see that the amount of light that's hitting the detector has dropped from 0.32% to 0.26%. That number, however, is not the number we're optimizing for. We don't care about that. We care about what's getting into the fiber and that number has gone up. But this number is also somewhat deceiving. And understand that we want to look at the improvement that we've gotten across all of the wavelengths that we care about, because there are some massive improvements hiding in the ultraviolet and the other wavelength ranges. So let's investigate that now. To do that, I'm going to create another emission, but it'll be a single wavelength emission, another collection analysis tied to that emission, and then a scanner to drive them. Let's go ahead, point source, single. We'll start with 200. And yep, that all looks good. Oh, I forgot to add the light path. Boop. Okay, then we're going to create a collection efficiency analysis. Detections only, filter the stray rays. Did I add that to the right one? No, I didn't. Okay, I'm going to add that. And then we're going to create a scanner. Now the scanner is going to drive this wavelength of the second point source from 200 all the way up to 1,000 over 50 steps, so it's nice and smooth. And for the output, we're going to care about collection efficiency to scaled efficiency. This is the actual collection efficiency. Go ahead and create that, and we're going to run it. Now this is a different shape from the previous design, but one thing that's immediately apparent is the area in the UV is remarkably higher, whereas this area may be less. And we actually don't see that sharp drop-off that we saw before when the cone moved, the light cone moved into and then passed through the profile of the fiber on the detector. So this is a materially different shape, and it's a lot better in the UV regime. Let's go ahead and download the CSV version of that. All right, now let's go back to the other previous design. Let's download a file from the same analysis. Okay, here we are in the other design. Let's go ahead and run that scanner. As we can see, a very different shape, higher peak, but also possibly much less collection efficiency in the UV. So I'm going to go ahead and download that. All right, so I've gone ahead and downloaded both of the CSVs, and I've opened them in this spreadsheet to the right. So in this column, I've got the wavelength that we scanned for both designs, both V5 and V5 with the achromat. And then I've got the collection efficiency from the basic design. This is the one with only 2 lens elements. And then I've got the one with 4 lens elements for our achromat. Now, if you take a look at the improvement column, which is just the ratio of the collection efficiencies, achromat divided by basic, you can see that the achromat has improved collection efficiency in the ultraviolet range between, say, 200 and 350 by between 6, 7, and 3x across the board. This is massive improvement, even though we didn't have a large amount of light in this to begin with. These are dramatic improvements and could make the difference. Also across the board, we note that many wavelengths are just doing better. There are some wavelengths between about 689 and 885 that are doing worse. This is where that peak is in this analysis. That's this peak area. And then we notice at the end where that peak drops off, we're doing better. So almost across the board, we're doing better. In some cases, we're doing much better. And only in a few cases are we doing a little worse. And this kind of behavior is to be expected with an achromat because it's trying to focus at 2 points, and that's all it can do. The points in the middle tend to be a little weaker, and it's these wavelengths that end up being in the middle. All right, so now I'm back at our achromat design. I'm going to go ahead and cast the rays just so we have a pretty view. And to sum up, here's what we did. We started by building a point source collection lens where we took what we learned from collimating light into optical fibers, and we essentially applied it in a mirrored design where we collected the light from the point source, we collimated it, and then we refocused it into an optical fiber. We noticed that when we did that across a broad range of wavelengths, we suffered heavily due to chromatic aberration. We addressed that problem by designing 2 achromats that corrected for the chromatic aberration and gave us much higher collection efficiency overall, but remarkably better collection efficiency in the ultraviolet range. Now this is where we will stop for this video. But I want to remark that there is one final thing we could do to improve things even further. and that would be to switch over from lenses to mirrors. A mirror-based approach would have no chromatic aberration at all. It would, however, be awkward physically because of the way you'd have to arrange the mirrors. For many applications, our first design with only 2 lenses is good enough. For even more applications, our second design would be good enough. But if you needed the absolute best performance across a wide range of wavelengths, going with mirrors might be something that's worth considering, and we will show how to design that in a future video. Either way, that's all for now. Thank you very much for watching, and I'll see you next time.